All right, in this video we're going to talk about joint random variables, covariance and correlation of joint random variables. First, we need to begin by defining joint random variables. These are the intersection of two random variables. So, if we had two random variables, which you'll remember we denote with capital letters, we'll call them x and y. When you're talking about joint random variables, this takes you all the way back to the intersection of variables. We're talking about all the probabilities that result from combinations of x and y. So we might say the probability of one of those outcomes is the probability that x, our random variable, equals a value of x, and the intersection of x equaling x and uppercase y equaling lowercase y. That's one possibility. And so what we talk about when we talk about joint random variables is the entire universe of probabilities associated with combinations of x and y. If you take every possible outcome for x and every possible outcome for y and match them all up, you're going to get a total probability of 100%. As with every any probability event, you're going to have a total possibilities of 100%. You just have to add up all those probabilities. Let's take a look at an example here. Let's say we have two events. We are rolling a six-sided die and we're flipping a coin, heads and tails, and 1 through 6. So we'll say x is rolling a die and y is flipping a coin. X would be defined as 1 through 6, y would be defined as heads or tails. We have a whole bunch of outcomes that are jointly associated with these. We can get a 1 on the die and we can get a heads, or we can roll a 1 and get tails. We can get 2, we can roll a 2 and get heads, 2 or get tails, 3 and get heads, 3 and get tails, and so forth. Turns out we have 12 possibilities here. And each one, and we're just multiplying. In this case, these are independent events. They have no influence on each other. So whatever I roll on the die is not going to influence what I flip on that coin. All 12 events have a probability of 1/12 happening. There's a 1 in 12 chance of me rolling a 1 and flipping a tails. A 1 in 12 chance of me rolling a 5 and flipping heads. And we've just multiplied the probabilities. 1 out of 6 times 1/2. And that's because these are independent events. However, if these were not independent events, we wouldn't just be able to multiply their probabilities together. Because let's say there was some association between them. Let's say there was some influence. What you got with your x and the outcome you got for y were somehow linked, and which is going to be the case in most of the random variables we're looking at, especially the joint random variables when we're looking at them together. There's usually going to be some relationship. And we have to define that relationship and figure out how it's going to influence the outcomes. And that's what we're going to talk about with covariance and correlation. So, covariance and correlation are both measures of the association between two random variables that are not statistically independent. They both show the association between the two variables. And when covariance and correlation are positive, it means that as one variable goes up, gets larger in value, the other variable also tends to get larger in value, and vice versa. So if one variable goes down, gets smaller, the other variable has a tendency to go down. A good example of this would be height and weight in people. So people who are taller tend to be heavier. Tend to be. They're not always heavier. So I'm 6'5", 220 pounds, and someone who's shorter than me will tend to be, but not always be, lighter than me. There's a positive association between height and weight. Someone who's taller than me will tend to be heavier than me. But again, it's not a perfect association. It just means there's a tendency. And the strength of that association will be shown with covariance and correlation as well. Another example. So I meant to write these down. So height and weight would be a example of positive covariance and correlation. Another example would be temperature and ice cream sales. So as the temperature rises, people tend to buy more ice cream. As the temperature falls, people are less interested in a cold dessert. So temperature ice cream sales. A negative association means when you have negative covariance or correlation, it means there's a negative association between the two variables. It means that as one goes up, the other one tends to go down, and as the other, and vice versa. So as the other one tends to go up, as one goes up, the other one tends to go down. So continuing our temperature and sales of various foodstuffs example, if we had temperature and sales of hot chocolate. Right? As temperature goes up, people don't really like to buy hot chocolate as much. If it's over 100 degrees Fahrenheit, people tend to not be so interested. But as there's snow on the ground, hot chocolate seems like a really good proposition. People do tend to buy hot chocolate. And so these have a negative association, meaning one goes up, the other one goes down, and vice versa. Covariance and correlation are basically similar measures. They both, by their signs, show the association, whether it's positive or negative. Negative covariance or negative correlation shows a negative association, negative relationship between two random variables. Same with positive covariance and correlation showing a positive association. But generally speaking, correlation is a little bit easier to work with because it's standardized. When you're talking about two random variables, correlation is always going to be between -1 and 1. So it'll be anything in the spectrum, -1 to 0 to 1. Whereas covariance can be sort of anything. So you can think of these a little bit like variance and standard deviation. Correlation is just a little bit easier to work with because it's standardized. All right, so let's focus on correlation here and talk about what, how to interpret a correlation of -1, 0, 1, all those things. So if you have a correlation of -1 or 1, or +1, it means there's a perfect association. It doesn't mean there's a linear association, but it means that there's an entirely predictable relationship between the two events. Meaning if one goes up, the other one is going to go up. If this is a perfectly positive association, it means the other one's going to go up by an exactly predictable amount. Again, doesn't have to be 1-to-1, but it is going to be a linear association. So, for instance, say the radius of a circle and its circumference. Right? The relationship, I assume everyone knows this, is 2. The circumference of a circle is 2 times the radius times pi. So 2 pi r. And so that's going to have, if we plotted this out and we showed the circumference over here and we showed the radius down here, we took circles of various radii. I don't know if that's the plural of radius. I'm just going with it. We plotted them out. It's going to be linear. And the slope of that line is going to actually be 2 pi. So whatever the radius is, multiply that times 2 pi, and you're going to get the circumference. So again, not a 1-to-1 relationship, but an entirely predictable relationship. This is perfectly positive, and so this is going to be a correlation of 1. Another example would be temperature in Fahrenheit and temperature in Celsius. The relationship here is just 9/5 plus 32. Convert from Celsius to Fahrenheit. Again, not 1-to-1, but it's entirely predictable. If you know what the Fahrenheit is, you can absolutely get the Celsius. If you know what the Celsius is, you can absolutely get the Fahrenheit, and you'll know exactly. So it's going to be if you plotted this out, Celsius and Fahrenheit or vice versa, you're going to get a straight line, 100% predictable. So it's a perfectly positive relationship, a correlation of 1. And of course, you can have the exact same thing with a perfectly negative relationship, a correlation of -1. So an example of that would be the amount you donate to charitable causes versus the amount you pay in taxes. As long as you're within the same bracket always, your taxes are going to be affected in a completely predictable way. So amount you donate, and taxes you pay. The more you donate, the less taxes you're going to be paying in an exactly predictable relationship. It's always going to be the exact same. Your taxes are always going to be reduced, again, provided you're in the same bracket the whole time, always going to be reduced by the same amount according to the amount you donate. So no correlation just means there's no predictable relationship between the two variables. So it doesn't actually mean that they are statistically independent. This is a funny distinction, but statistically independent events always have a correlation of 0. But basically it just means you can't. There's no association that you can predict. You won't know. Sometimes one might go up, while the other one might go down. It's impossible to predict based on the two variables. So I'm going to write down here includes statistically independent events. Statistically independent events. But that does not mean that all events that have no correlation are statistically independent. Oh, also, I want to write down here that no correlation, it means correlation of 0. And of course, perfectly negative correlation is -1. All right, now I want you to be familiar with what the extremes in terms of possible correlations between two events are. That'd be 0, -1, and 1. But most of the events you're going to be looking at are going to have some association. If they're not statistically independent, they're going to have some association, but it's not necessarily going to be perfect. So examples would be the performance of the New York Stock Exchange versus the performance of an individual stock. There's going to be some relationship, with most stocks, though not every stock. As the New York Stock Exchange goes up, individual stocks are going to rise as well. There are examples of stocks that have a negative association, but again, it's not going to be a perfectly negative association. So some stocks tend to go up as the New York Stock Exchange goes down, and goes down when the New York Stock Exchange goes up. But again, not a perfect relationship in either case. Going back to our previous example, height and weight in people. There's certainly an association. Very tall people tend to be heavier, and very short people tend to be lighter, but it's not at all perfect. The amount of time that a student spends studying on a test versus the grade they get on that test. There's a positive association for sure, but some students, those people who just don't study at all and do great. Or there's people who study a lot, and maybe that test just didn't work out for them. An example of a negative correlation that's, again, not a perfect, so somewhere in between -1 and 0, would be the amount of world oil production versus gas prices. So as oil production tends to go up, gas prices tend to fall because there's a lot of supply. As oil-producing countries cut back on production, gas prices tend to rise. But again, these are not perfectly predictable relationships. It's not going to be -1 because there's things like speculation in the markets and other things that can drive up or reduce gas prices that are sort of unrelated to oil production. Related maybe, but it's not a perfect association by any means. So let's take a look at some examples, because I want you to be sort of familiar with being able to generally eyeball looking at a scatter plot. So you've got two variables on each of these graphs. You've got two variables. One's going to be charted along the x-axis, and one is going to be charted along. One is going to be charted along the y-axis, and the other on the x-axis. And each of these points represents a joint probability: one value of x and one value of y. And these are sort of our universe of combinations here. Obviously, if you were to take a line and put a best fit line through your data points, if that line has a positive slope, you're going to be dealing with positive correlation, positive covariance. If the line would have a negative slope, you're going to be dealing with a negative association. That just sort of makes sense. The better fit on a line, the closer you're going to be to 1 or -1. So, as I showed you earlier, if we draw one of these and the dots go like this, that's going to be a positive, that's going to be association. Well, it's not exactly on a line, but this is basically a correlation of 1. Or if we drew 1 and the dots went like this, that's a pretty good one. That's going to be a correlation of -1. So these show, this is a strong positive correlation and this is a strong negative correlation, meaning the data points are almost linear. Challenge question, which one do you think is a stronger association? It's this one. This is clearly more linear. Sure, it's negative, but that still indicates a strong negative association, and it's more linear than this one. This would be a very weak positive correlation, but you can see there is a relationship. This isn't just a cloud of dots. That would be here, where we have just a cloud of dots, meaning it's entirely unpredictable. If you were to draw a best fit line through that cloud, I don't know, I mean, it could go like this, or really anything. It's basically impossible to define the association. And so therefore, we say this would be a correlation of 0. And you have various degrees of strength in terms of the correlation. And again, we say it's a strong correlation even if it's negative. So a strong correlation could be something very close to -1, just a strong negative correlation. All right, here's examples that show actual values. R is defined, correlation, it can be shown as R. Lowercase r here represents the correlation. And so I just want you to have a look at this, sort of figure out, how, sort of a measure of how the correlation would look as in representation of a scatter plot. So we can see this is a fairly weak positive correlation. Yes, there's a relationship, but it is kind of cloudy. Over here, much stronger. And so you can imagine if we sort of brought those dots in even closer to the line, it would be an even higher positive correlation. And again, we see examples of 0 correlation when it's just a cloud. It'd be impossible to draw a line through it. Also, another interesting thing to point out is if you have something like this, totally linear, right? But if the line is completely horizontal, you're also going to have a correlation of 0 because you won't be able to predict anything based on your x value. So no matter what your x value is, you're always going to have the same y value. So there's no predictive relationship. So another example of 0 correlation. Anyhow, I hope this gives you sort of a sense for how correlations shake out, and you could sort of maybe eyeball a scatter plot and say, oh, I think this is a correlation of -0.5 or something. It's not going to be something that you have to be exact about. Just give you an idea. All right, so I'm going to do an example that shows you how to calculate correlation and covariance. These are important equations that I really want you to write down. The equation for covariance, you actually have 2 equations for covariance that basically amount to the same thing. You can kind of use either one you want. I like the top one, but do write down these equations, think about what they mean, and the equation for correlation here, which includes, you'll notice, covariance in it. So definitely pause this video, write down these equations if you don't have them already in front of you. And we're going to do an example now showing these. So in this example, let me bring it up here. We are going to be looking at a company's monthly sales figures as compared to their marketing spend. So every month they're spending a certain amount on marketing, and then they are recording their sales figures for that month, and they want to know, what's the relationship between the amount we spend on marketing and our monthly sales. You'll notice on this spreadsheet that I've kept the equation, my favorite equation for covariance, though you can use either one, and the equation for correlation here. And we're going to manually calculate the covariance and correlation, and then I'm going to show you how to do it using Excel's handy shortcuts. But first off, let's do a little sanity check here, just sort of quickly make some predictions. Based on common sense, we would expect there to be a positive relationship, right? Like the more you spend on sales, the more you spend on marketing, the more sales you're going to generate. Hopefully that's the case. I did a scatter plot of this data, and down here on the x-axis we have the marketing spend, on the y-axis we have the monthly sales, and I drew a best fit line. I didn't draw, Excel put a best fit line through this data, and you can see that there is it's pretty linear. It looks pretty good. You know, this line is going to be a fairly excellent predictor. So, what does that tell you about what we would expect the correlation to be? Well, first off, we expect it to be positive. And looking at this, I would expect it to be pretty close to 1. You know, this is not a great big cloud of points. This is actually points that almost line up. So the closer they are to linear, to an exactly linear relationship, the closer the correlation is going to be to 1. So we are expecting this to be a positive correlation that is pretty close to 1. All right. So let's start out by calculating the covariance, which we're going to have to do since covariance is in our equation for correlation. I'm going to start off. We need the expected value of x times y. And so what is the expected value? It's the average. That's all it is. Finding out, and sometimes it's a weighted average, but really the expected value is just an average. So let's keep everything in line here. I'm going to write x times y. This is going to help us get the average here. So first off, I'm going to set this up so we're calculating each of these values. Let's set this up so that that border doesn't disappear every time. And I need an average here. So I'm going to go in here and write average, and I'll get to that in a moment. Average of B2 to B13. Okay, so this is my expected value of x times y, monthly spend times monthly sales, right? That's the first part of my equation. It's just the average of, you know, each of the multiplication of those two data points. That's it, the values that are associated with each of the data points. But now I actually need the averages of x, and I need the average of y as well, so we'll just drag this over. So far, so good. And so now I should be able to figure out my covariance. So go down here, write covariance. And this is going to be equal to my expected value of x times y minus the average for my marketing spend times the average for my monthly sales. That's my covariance. Now we need to figure out what the correlation is going to be. Okay, but for correlation, we're actually going to need standard deviations. So let's figure out what those are going to be. Wait a second, is that, yeah. Oh, I forgot to label this. STD, standard deviation. And we'll just drag this across. So now I have my standard deviation for marketing and monthly sales. My correlation is going to be my covariance divided by standard deviation of x times standard deviation of y. And let's reduce some of these decimal points. And correlation to 0.95, 0.952 if you want to get closer. So does that match what our predictions were? Yeah, absolutely. You know, we were predicting something, a positive association that was close to 1. We're looking good. Now, let me just show you the quick shortcut using Excel functions, which you probably already knew about. We're going to just use covariance here. It wants the first array, which is going to be the covariance between these two variables. I'm just going to go ahead and grab these. Exact same number. Everything's checking out. Do the same thing with the choral function. Lovely. It all works out. So that is an example of using Excel. I mean, you could do this by hand if you had to, and using these equations to calculate covariance and correlation.